the regrading in this week. Okay. Okay, so today we're gonna wrap up the linear regression topic. So to refresh our memory, let us start with definition of regression. So basically, we start with the general regression problem, namely that we have several variables, say x1 to xd. And we want to use these d explanatory variables to predict our interested variable, denoted by y. So these d variables are called explanatory variables, and y is called the dependent variable or target variable. So the prediction procedure is called regression, but regression means that the dependent variable or the target variable is continuous, is real value. If it is a discrete value, like binary, like order, it is really referred to as classification. So this is the definition of regression. And then we define the concept called linear regression. So what is linear regression?
When you're trying to find a regression after a linear function.
Yeah, exactly, right? So as the name suggested, what is linear regression? Meaning that we want to use a linear function to express the relationship between our target variable and our explanatory variable. So in our regression model, we usually use a function of our explanatory variable to model or interpret or fit the target variable y. Right? For linear regression, this regression function is expressed as a linear function. Right? So what's the general form for this function? What's the general form? Any clue?
So do you mean just the wave vector times each x1 or x point? So like alpha 1 x1 plus alpha 2 x2.
Yeah, exactly, right? So no matter when we are asked for a linear function, you can what kind of things should come out in your mind. So first we have an intercept. We have a constant. It's alpha 0. So you can just imagine a line in a two-dimensional space, three-dimensional space, or even high-dimensional space. So first we have an intercept of 0. And then for each explanatory variable, we introduce a weight. So for x1, we introduce the weight alpha 1, right? And then multiplying with x1. And then for x2, we introduce the weight alpha 2. And we can continue until the d explanatory variable, we introduce the weight alpha d, xd. So this is the general form of our linear regression function. And then we discuss to re-express it as a matrix vector operation, right? For succinct, for brevity, right? And for convenience of derivation. So we can express it as an inner product between two vectors. So what will be the form of the inner product?
Alpha 0 and then 1 and x1 x2 x3.
Yes. So whenever when we say this summation of the pairwise products, we can turn them into an inner product. Right? To do the inner product, we should first form two vectors. Right? So the first vector, we call it input vector. So what is the input vector? What is the first element of the input vector? Yeah, 1, right? This constant 1 is to account for the intercept alpha 0 here, right? And then the second would be the explanatory variable x1. And third will be x2, and continue xd. So our input vector will be a d plus 1 dimensional column vector, because we have to augment the explanatory variables with this constant 1 to account for this alpha 0. And correspondingly, we can form a weak vector. Right? So what is the weak vector? Yeah. So the weak vector consists of all the parameters, right? From alpha 0, alpha 1 to alpha d. So the first element will be alpha 0, alpha 1, alpha 2, continue, alpha d. So this is also a d plus 1 dimensional vector, column vector. And then, given these two vectors, we can write this linear regression function as an equivalent inner product. Right? Inner product between our input vector and our weight vector, alpha arrow. Then a key problem or key question in linear regression is to estimate or to find out the best weight vector, namely alpha arrow here, right? So how can we find it? We must first prepare a set of training instances. So assume that we have observed n training instances. So what is training instances? Namely, the pair of the explanatory variable values and dependent variable values. So suppose we have collected n such pairs, so denoted by x1 arrow, y1, x2 arrow, y2, until xn arrow, yn. So each input vector here is the augmented version for the corresponding instance. So, for example, for a particular input vector for the ith instance, so xi arrow, this vector actually consists of the constant 1, right? And also the values of the corresponding d explanatory variable values in ith instance. So xi1, xi2 until xid. Right? So xi1 means that the value of the first explanatory variable in ith instance. Right? xi2 means the value of the second explanatory variable in ith instance until xid. So now, suppose we are giving these n training instances. How can we find out the best weight vector alpha arrow to fit the n training instances? What's the strategy?
Objective function and divide analytic solution.
Yeah, we will form an objective function. So what's the objective function? Yeah, I heard someone. I heard the answer, right? So SSE, it's called SSE. SSE on this n training instances. So what's the definition of SSE? Its full name is sum of squared error over the n training instances. So as the name suggested, it's a summation over each training instances. And inside the summation, we calculate the square error of using our linear regression model to predict the dependent variable value. So it is yi subtracted by our prediction, which is xi arrow. This is the input vector. And in the product with our weight vector and take square because this is square error. So the process to fit our regression model to this n training instances is turned to minimizing this SSE. So to find out the best alpha vector is to minimize this SSE function, and we have shown that to minimize it, we can simply take the gradient of SSE with respect to each element of alpha vector and set the gradient to be 0. Right? And then we can solve the optimal weight vector alpha arrow. Right? And we spent quite nearly the whole lecture to show how we derive that. And we arrange the results into an elegant matrix form. Right? So here I won't repeat it again. So I just give you the results. So the optimal weight vector, which minimizes the SSE on the training set, turns out to be x transpose x, the inverse x transpose y. So here x, the matrix x and vector y is the input matrix and output vector y. Right? So what's the input matrix? What's the form of the input matrix? So how can we construct this input matrix X?
It's just a matrix in which each row is one example x vector.
Yeah, exactly. So we simply stack all the input vectors into rows. Right? Then we'll get our input matrix. So the first row will correspond to the first instance, the input vector for the first instance. So the first row will be written as x1 arrow transpose, because x1 arrow is assumed to be a column vector. So if we stack them by rows, we should do the transpose. And similarly, the second row corresponds to the second input vector. So it's x2 arrow transpose. And we can continue until the last instance, which is xn arrow transpose. So that means the input matrix X is a n by d plus 1 matrix. Why? Because each input vector is d plus 1 dimensional. Because we have to augment the original dependent explanatory variables by the constant 1, right, to account for this intercept. So this is a definition of the input matrix. Then what is the output vector y? An idea?
The result of each of those instances.
Result of what?
The result of one instance.
Yeah, the result actually is the value of the dependent variable or the target variable. So the output vector y is simply put all the dependent variables values together. So we have n dependent variable values because we have n training instances. Right? So the output vector is n dimensional output vector. So this is the result of our general linear regression. And then after the introduction of the general linear regression, so here, you should be aware that we can set D to be 1, meaning that we only have one dependent, we only have one explanatory variable. It reduces to the simple linear regression, but this solution still holds. And you can compare what you have derived for simple linear regression results, and actually they are totally equivalent. And so after the introduction of the general linear regression, and then we introduce the simplest nonlinear regression model. And for nonlinear regression. And in nonlinear regression, we only discussed the simple regression case, meaning that we only have one explanatory variable, say x, and we just want to use this single explanatory variable to predict our dependent variable y. Then what kind of a regression function we have discussed? Yeah, polynomial, right? So this is actually a natural extension from linear regression. So we use polynomial regression to model the possible nonlinear relationship between our target variable and explanatory variable. So then we need to specify the degree of polynomials. So we use the subscript p to denote the degree of the polynomial, and then what is the regression function? So what's the general form of the pth order polynomial function?
Alpha 0 plus alpha 1 x plus alpha 2 x
Yes.
squared.
Yeah, exactly right. So actually it's just a weighted summation of the polynomial terms from the 0th order to pth order. That's the general form of the polynomial function. So alpha 0 corresponds to the coefficient of the 0th order. 0th order polynomial term is actually 1, constant 1. So we do not need to explicitly write it down. So then alpha 1 multiplying with x to the 1, so it's x itself. Then alpha 2, x squared, alpha 3, x cubic, and continue until alpha p, x to the p. The pth order polynomial. And if we explicitly designate pth order polynomial, we should ensure that the coefficient for xp, x to the p, should be non-zero. So you can see this is actually a natural extension of the linear regression, because when we set p equals to 1, the polynomial regression is reduced to a linear regression. Right? Linear regression. And then the next question would be, how can we find out the best weights, polynomial regression weights, to determine our polynomial regression function? Again, assume that we have collected n training instances. So it's x1, y1, x2, y2, xn, yn. Then how can we fit our polynomial regression to this n training instances? How can we do that? Any clue?
Construct a polynomial version of the x vector.
No, we're not going that far away right now. I just want to ask if you are given this pth order polynomial regression function and you are given n training instances, how can you find out the best regression weights? What's the general strategy?
Same way.
Yeah, the same way. What's the same way? More detailed? again, we need to construct an objective function, right? So what kind of objective function do we use?
SSE.
Yeah, SSE, right? So we still use this function. The only difference is that we need to change our regression function from the linear regression to the polynomial regression. Right? So just switch, just remove the regression function here and replace it with our polynomial regression function. That's it. And then we minimize this SSE again on the training data set. And then we take the gradient of SSE with respect to each polynomial regression weight and set the gradient to be 0. We solve it, we end up with our optimal weights or coefficients here. They follow the same strategy. And actually, if you want to practice your manual derivation capability, you can do it again. Right? But right now, we're not interested to reinvent the wheels. We discuss a trick to directly use the result from linear regression. We don't need necessarily, we do not necessarily need to take the gradient set and solve the gradient to be 0 again. And then what kind of trick did we discuss? Any idea?
Transform the X vector from linear to polynomial version.
Can be more explicit?
Here, when we in the linear regression case, x1, x2 to xd is one dimension in one power of 1, but in this case we have polynomial version, so we just put the linear regression to the polynomial version.
Yeah, you're right. Right. So let me rephrase it again. Right. So our trick comes from the observation of the form, of the regression function form. Right? So we can say this polynomial regression function, although it is a nonlinear function, but it can still be expressed as an inner product between two vectors. So what is the inner product? We can define two vectors as well. Right? So the first vector, we still call it the input vector, but the input vector consists of the polynomial transformations of the original explanatory variables. So the first element is simply 1, which is the same as our linear regression case, because we both need to account for the alpha 0. And the second is here, right? X. And third is x squared. And we can continue until the last term, which is x to the p. So this is our input vector. And then we can also construct a weight vector, which is exactly the same as the linear regression model here, right? Consists of alpha 0 to alpha d. But here we are, because we are designate a p dot polynomial, so our weight vector will be alpha 0, alpha 1 to alpha p. So by defining the two vectors here, our polynomial regression function can also be expressed as the inner product between our weight vector alpha arrow and input vector x arrow. Right? So we can say both regression functions have the same form. Then if you are given n training instances, and we have the similar SSE form, right? We have the same SSE form. So here you can simply write it as alpha arrow and the input vector x arrow. Right? This is actually has the same form as the SSE of the linear regression. That that means if you do the gradient calculation and solve the gradient equation that gradient being 0, we must have exactly the same form here. Same form solution here. Right? And then the question is that how can we find out the corresponding input matrix X and output vector Y for our polynomial regression problem? So then what is the input matrix X for our polynomial regression problem?
It's just a combination of the X vector for that.
Yeah, it's exactly similar to the construction of input matrix for linear regression, right? Except that each input vector is now taking this kind of form, taking the polynomial transformations of the original explanatory variables. So we still use this form, but for each input vector, xi arrow, it becomes what? It becomes a form like this. So the first element will be 1, and second is xi, and the third is xi cube squared, and fourth will xi cubic, and continue until the last is xi to the p. And then the first row corresponds to the input vector, which are the transformed polynomial transformation of the first value of the explanatory variable, right? Similarly, the second row, x2 transpose. The x2 transpose, the input vector x2 is transformed explanatory variable values according to these piece polynomial terms. And we can do it together until the last instance. And then what is the output vector y? What is output vector y? Yeah, output vector y is the same as the output vector y for the linear regression. It just consists of all the values of the dependent variable. And then, given our input matrix X and output vector Y, we just perform the same computation to obtain our polynomial regression weights. Any questions so far? It's just a review of what we have discussed in the last 2 or 3 lectures. Okay, so next I will show you how to write a piece of Python code to implement our linear regression and polynomial regression model. Is it clear for anybody? For everybody? It's not clear. Can I enlarge it? Does it look good? Okay. So here I give you a simple example of implementing your own linear regression model with multiple explanatory variables. So here in this simple problem, we have 3 explanatory variables. So if you have spend some time reading the course material, actually there is an interesting application of the linear regression problem. Namely, we want when the customers view some website, and the website sells out the dongles or the adapters. The website, the company which runs the website wants to predict how much money the customer will purchase the adapters or dongles from the website by using 3 features or explanatory variables. So here I just copy the data and store them in matrices, in numpy matrices and the numpy vectors. So we can first take a look at the form of data. So here are the so here this is an input matrix X. So each row corresponds to 1 instance. So the first column, second column, 3 columns are the values of the 3 explanatory variables, and we can see there are 1, 2, 3, 4, 5, 6. There are 11 rows, meaning that we have 11 instances. And the vector at the bottom represents the dependent variable values, namely how much money the customers purchase in cents to buy the adapters in that website. So this is our data. And then we want to learn a linear regression model to fit the data, right? So before doing this, we need to first augment our input matrix by 1s, right? Because we need to account for the intercept alpha 0, as we just mentioned. Now how can we do that? And we can simply call the numpy.hstack function. Hstack function simply merge the 2 matrices horizontally. So you can imagine that there is a long vector full of 1s, and then you merge them with our original input matrix, such that in each row we have inserted a 1 in front of all the 3 explanatory variable values. So we can run it and see the augmented data. So here is the augmented input matrix. So we can say, although this layout looks ugly, I don't know why we want to represent that in terms of the power form. So, but we can say each row we insert a constant 1 to account for the intercept parameter alpha 0. And y doesn't change. And then to find out the optimal weight vector, we can implement the computation of our optimal vector alpha. Right? So the optimal vector alpha, it is covered by. So it is here. X transpose X inverse X transpose Y. So actually we perform 3 matrix product. So first calculate the product between X transpose and X. Right? Then take inverse and then multiply this inverse with X transpose. And finally we multiply this matrix with the output vector Y. So we just need to implement this matrix vector operations in our Python code with numpy library. So we can say the first inner product, the first product is between X transpose and X, right? And then we need to take the inverse of X transpose X That's why we call the inverse function. So LA here is a brief name for the sub-library of the NumPy. It's called linear algorithm library. Right? We rename it as LA for brevity. And then after we're doing the inverse, and we multiply this inverse matrix with X transpose. That's the second product. Right? And then after we doing this, finish this second product, we do the third product. That is multiply this matrix with our output vector Y. And then we end up with our optimal big vector alpha. This is how we implement our training procedure to obtain our best big vector alpha. And then we can take a look at the exact value what we got. We can run it, and here's alpha. Here's alpha 0, corresponding to the intercept, and alpha 1, alpha 2, and alpha 3. Because we have 3 explanatory variables, so actually we have 4 parameters. The first corresponds to the intercept, alpha 0, and then the remaining 3 are for each of the 3 explanatory variables. So this is an explicit implementation. Sometimes, if you want to avoid it, you can directly call the internal function provided by the NumPy library. It is called least square function. So the name is LSD SQ. So you can feed this function with our input matrix X and output vector Y. And here, what I said, the parameter, our condition to be done is to avoid the warning message. It's kind of useless things. And this function will return you several stuffs. The first return result is our optimal bit vector. And second, third include the training SSE, for example. So you can check for the documents and see the detail. So we can instead run this least square function to get our estimation of the best weight parameters of linear regression, and we run it, and we can see nothing changed here. So the two implementations are exactly the same. So I will share this this code snippet in the canvas, because in our homework 3, you are required to implement your own least square linear regression model on some designated data set. So this is for the linear regression. And then we can take a look at the polynomial regression. So how can we implement polynomial regression? So here I give you another example. So here, X and Y, if you still have impression, we have gone over an example by using a person's height to predict its weight. And at that case, we simply use a linear regression model. But obviously, we can use a polynomial regression to finish the prediction. So here, I just copy the input data and the output weights. The input data consists of the heights in inches, and the output are the weights in pounds. So we can take a look at the data. So this is X and this is Y. And to implement your polynomial regression, you can do the direct computation. That is, we first do the transformation of the original explanatory variables, right? To transform them into the input vector and stack them together to get your own input matrix, and then call the same computation procedure as in the linear regression to compute the optimal polynomial regression weights, as we just mentioned, right? But here there is a more convenient way to do that, because the Scipy library provides the polynomial regression fit function. It is called a polyfit. So we can simply give this function our input vector x and the output vector y and specify the degree. And then you can get the best coefficients or weights for the polynomial regression function. The problem is that the return alpha, the coefficients are for the polynomial with the highest order to the lowest order, meaning that the first element in alpha is the coefficient for the polynomial term with the highest order. So the last element alpha is the coefficient of the constant, the zeroth order polynomial. So we can simply we can start with degree equals to 1, meaning that we are doing a linear regression. So we can take a look what is the coefficient we can learn by doing polynomial regression, and what is the regression function. So here is the alpha, the estimated alpha. So the first element alpha corresponds to the coefficient of the highest order polynomial term, which is the x to the 1, right? It's x itself, because degree is 1. So this is actually the slope. And the last element in alpha corresponds to the intercept, right? The zeroth order polynomial terms coefficient. So that is here. So we can change the degree to 5, right? You can freely change it and run it. So this is alpha. This is the alpha we estimated, and this is the corresponding regression function. So any questions so far? It's pretty simple. Just a few lines of code implement our polynomial regression and linear regression with multiple variables. And this code will also be shared in the canvas for your reference, and you can play with it. So let us shut down the projector for a while, and let us continue. So there is a property of the polynomial regression, which actually we should have already known that, like in our high school. But today, maybe the first time we know it's using, especially data science. So to identify a specific p-th order polynomial, how many distinct data points do we have? Do we need to have? So suppose we're given a p-th order polynomial, right? And to determine the parameters alpha 0, alpha 1 to alpha p, so how many distinct data points do we have? Do we need to have? P plus 1? Yeah, exactly. Right? Because we have a p plus 1 unknown parameters, right? So to identify this p plus 1 unknown parameters, we need at least p plus 1 distinct data points. Right? So that becomes a problem. Let us think this problem reversely. So suppose now we have n training data points, x1, y1, x2, y2, until xn. If we want to use polynomial regression, we need to specify the degree of polynomial p. And remember, our strategy is to fit this n training instances is to minimize the SSE. So now, if we want to minimize SSE to be as small as possible, then what is the choice of your P? What is your choice of your degree of polynomial? An idea?
Close n, because we just mentioned that the number of weight factor greater than the number of the data set. It is meaningless.
Yeah, you're right. So if we have an n distinct data points, means that we can use this n distinct data points to identify a n-1 degree polynomial. Because n-1 degree polynomial will have n parameters of 0 to alpha n, alpha 0 to alpha n-1. Then what will happen to the SSE? If we choose the degree of the polynomial to be n-1, what will happen to the SSE on the training data set? Yeah, it will be 0. That's perfect, right? That sounds very perfect. Because these n data points can uniquely determine this n-1 or the polynomial, meaning that this n-1 or the polynomial will fit every single data point in this training set, meaning that the SSE on the training is simply 0. The question is that whether we encourage or whether we're happy with the fact that the SSE is 0. Are we happy? I heard no. Can I explain why?
Because what if you get a new data point, it might not fit.
Why?
Because it's too specific on the model.
Yeah, you can have an intuition that you are doing so good, too good to fit the. You are doing too good, right? You fit the training data set so perfect. Right? What will happen that because you fit your training set so perfect, such that when you predict a new data point, your performance will be worse. That could be a risk. But why there is such kind of risk? What's the root reason for such kind of risk? Your intuition is correct. It's perfect. It's right. But why that would incur some kind of risk? The reason comes from the noise in the data. So up to now, we always assume that, okay, those y1 to yn are the true values of the corresponding dependent variable or target variable values. Actually, this is often not true in practice. So due to a lot of reasons, like errors in devices or errors of the recorders, there are always kind of unknown errors in the data. For example, when you use some devices, when you do some biological experiments or chemical experiments, there are always some measurement errors in your device, right? Your device is not guaranteed to be 100% accurate. Also, when you write down the experimental results in your notebook, you're easily distracted, right? You might be distracted by like yesterday's movie or your vacation plan in a fall break or in a winter break. It is often possible. So actually, nearly in 100% scenarios, you can never assume the data is noise-free. Actually, it is always noisy. And even worse, you even don't know what kind of noises you have. How can you model noise? Then what happens if you still fit a set of training points which is full of noises? That actually implies that you not only fit the data itself, you also fit the noise. That means the noise actually guide or dominate your linear regression model, polynomial regression model, whatever other regression models. The consequence is that usually those noises will lead your regression model to a very bad performance. So to give you a intuitive example, So suppose we have a bunch of data set, right? This is training data. And unfortunately, the dependent variables values are corrupted by some noises. And you even don't know which one is corrupted by how much noises. You don't know. But if we use enough high-order polynomial function, we can ensure that our polynomial regression function perfect fit all those noisy observations, meaning that we end up with a function curve looks like this. So it should pass all the training data. So you end up with very vivid curve, right, to pass all the training points. But what if here, let's just look at one training example as an example. Right? What if this training example is corrupted by a very large noises, and the true value is here? So if your data point is not corrupted by some noises, then your curve should be like this. Right? You should pass this true data point without any noise. But now, due to the corruption of noise, you jump. You jump largely. So now let us consider the prediction performance. So suppose this part of the curve is the real curve, the real regression function value. So now if we want to test a function here, which is near this input, and the true value is here. But because we overfit the training data, this is our learned regression function curve. Our prediction are here. So now we can see the error. We can see the error is here. Right? The error is amplified. If otherwise we do not fit the training data so well, like we have a kind of trade-off, right, between the extreme fit and the true function curve. Say we have a curve like this, right? So that we do not perfect fit the noisy observations, then our prediction will be here. There is still some error. The difference here, right? But the difference will be much smaller than the curve that overfit the training observations. So this is one example showing that how your overfitted model can make your prediction worse. The question will be, how can you avoid overfitting? So here, we define if your SSE on training set to be very, very small, say close to 0 or even being 0 as overfitting. And the practice showing that overfitting is really not a good sign, meaning that you have a very poor general performance. Then the question is that how can you avoid overfitting? How can you avoid overfitting? The reason to incur overfitting is that we use just one measurement to measure the performance of our model. The measure is the SSE on the training data points, right? But actually, we only care about when we use our trained model to predict the future on same examples and where will be error. No matter how good you are performing in predicting the training examples, we do not care. We only care about the general performance, right? When you use your trained model to predict some new data points. That comes out a very general, empirical, but very effective solution to avoid overfitting. So basically, for these n-training instances, the original n-training instances, we do not use them all for training. Instead, we randomly split the n-training instances into two parts. One set So let us denote this n data points as d, right? We split the n instances into two parts. We only use one part for training, and then use the other part for test. So, but we need to ensure, of course, we need to ensure the test subset and the training subset is not overlapping, and also the training subset and test subset, their union is our original data set. And then we train our model on this training subset. And then to test its general performance, we calculate the SSE on this test subset. We use the SSE on test subset to indicate the general performance. In this case, we can imagine that even our SSE on the training subset approaches to 0. If its performance, namely SSE on the test, is worse, we can judge that this polynomial regression model is not good. We should we should try another degree of polynomial. So this is the basic idea. So this is called cross-validation. Because we split the test and training. We do not make the test and training subset to be overlapping. And how can we choose the size of training and test subsets? So there's an empirical ratio. Usually you choose the test subset to be 10% to 33%. That is 1/3 of the whole data set. So now we can take a look at this. Is a very simple strategy, but works very well. It's very widely used in the model selection procedure in practice. So now let us look at an example. We implement this cross-validation. Suppose we have a, is it clear for everybody? Suppose we have originally we have 9 points in total, right? And we can try, and we do not use cross-validation. We just try different order polynomials and to fit the 9 data points. And those blue dots represent the 9 points, and the red curve are the fitted polynomial. So we start the degree to be 1, meaning that we're using a linear function. So it ends up with a line. Right? You can see this line is near to all the 9 data points, but rarely directly fit every point, right? And then when we increase the order of polynomial, say, to 2, you can see this curve is much closer to the 9 data points. And when we continue to increase the degree to like third order polynomial function, we can say we get even closer. And when we increase, we can say, okay, your polynomial regression function is more and more vivid. At the same time, it is closer and closer to all the data points. And finally, if you use 8th order polynomial, as we just mentioned, right? N data points can determine n-1 degree polynomial. So you can say this 8th order polynomial actually can pass all of the 9 data points. But this is not a good sign. Although the SSE on the data points right now is 0. obviously, right? Because it crosses it passes all the 9 data points, but it might indicate the overfitting problem. And then how do we solve this problem? We can split these 9 data points into 2 parts. One part is only for training, and the other part is only for test. Right? So here is our cross-validation implementation. So here, I randomly pick up 6 points as the training subset, then leave the remaining 3 points for test. Then we only evaluate the SSE on the 3 test points and to verify its general performance. Right? So here's the training and test, and here we can set up a different degree of polynomial, and the implementation of cross-validation is in this function. It's called plot poly. So we can go through the implementation of this function. So plot poly, the input consists of the training subset, are x and y, and xe, ye are the test subset, and p is the degree of polynomial. So because we want to show it in figure, so we first draw all the training points, which are marked as blue points, and the market size is 80. And then we also draw the test points, which are marked as green points, and size is 50. And later we will say they are different. And then we set the axis, the range of axes, to make them to cover all the training and the test points. And then to fit the polynomial, again we use the polyfit function. We just show it. Right? And then to draw the curve of the polynomial function, we sample a set of inputs. We use this function called linear space function. So basically, you just split the segment between 0 and 10 into equal space into 101 points as the input, and then this function actually returns the polynomial function by using the coefficients we just obtained. And then we evaluate this 101 input using our polynomial function. We get our polynomial function values, and we plot them together. We end up with our curve of polynomial function, which is a red curve, and later we'll see. And then to evaluate the general performance of our fitted polynomial, we use our test subset. Right? This is our key idea of cross-validation. So how can we do that? We just use our polynomial function to predict the value of the test input, xe. This is our result. And then we compute the SSE on the test set. So basically, we compute the square error of the dependent variable values subtracted by our prediction and take square, because it's a square error, right? And sum together, we get SSE on test. And we print out the degree of our polynomial regression function and also the SSE on test in the title, and finally show it. So this is the basic logic flow in our implementation of cross-validation. And now we can try to play this function. So any questions so far? It's pretty straightforward, right? It's too easy to have any question on that. Okay, that's good. So we can start with degree 1 polynomial, which is a linear function, right? So we can see what can we get. So this is a degree 1 fit. Those big blue dots represent the training subset, and blue small dots represent the test subset. Remember, we have 6 data points for training, and the remaining 3 data points for test. And this red curve is our fitted polynomial regression function. And we can see our regression function has a larger prediction error to the test data points, right? So the SSE test is 8.227. This is quite big. That is mainly because our degree of polynomial is too small, right? It's a too simple function. So we underfit the data. And now let us try to use a more complex polynomial. We can switch the degree of polynomial to 2. And then let's see what kind of regression function can we get. We can run it. So now what can we observe? We can observe that our polynomial function is much closer to both the training data points and test data points, right? So look at the SSE test. It becomes it is reduced to 1.201. It's reduced, largely reduced. And to compare different orders of polynomials, we can further increase the degree. Right? We can try degrees to be 3. So now we can see the third order polynomial can get even closer to the training data points, but it gets further away from the test subset. And we can see that SSE test now is larger, 2.74, right? It's larger, meaning that the general performance actually is worse. So it's a sign of overfitting. And you can keep increasing the degree. Say, you can increase it to be like 7, like 8. Ignore the warning message, doesn't matter. So now we can see it overfits the training data. The training data, each of the 6 training points is passed by our regression function.
So once we see the error increasing with the degree of polynomial, will it continue to increase as we increase the degree?
It depends. Because for this polynomial regression, you can imagine that when you increase the degree of polynomial, your regression function becomes more and more complex. That means it has a larger and larger chance to overfit data. So usually you can just stop it. You just pick up the one which has the smallest SSE test. But for other types of regression functions, you don't have such kind of conclusion. Then you might need to try a various setting of the degrees or other hyperparameters and pick up the one with the best generation error. It refers to the SSE test here. So here I just want to show how we increase when we increase the degree of polynomial, how this overfitting phenomenon becomes more and more obvious. So we can see this is a very obvious overfitting because although the training SSE is obvious 0, but the test SSE now becomes 108. It's super large. Okay, and I also share this code in the canvas, and you can play it, and you can try different types of polynomials, and also you can create your own data set and see how this overfitting becomes more and more severe. So now from this simply from those set of trials, we know that we can simply choose degree of polynomial to be 2. That is enough. That's enough good, and has very good general performance. Okay, so the last point I want to mention about cross-validation is when the number of data points is small. So as we just mentioned, how do we choose the number of test subsets, right? We usually, there's an empirical value. We can choose 10% to 33% of the whole data points as your test subset. But what if you have very limited number of data points? Say you have only 5 data points. Even you just choose 10% of the data points, you end up with 0.5 data point for cross-validation. It's actually not even enough for a single data point. Then how can we deal with this case? How can we still want to perform cross-validation? And here we will use the strategy called leave one out cross-validation. What is leave one out cross-validation? Simply, each time we only pick up one data point out of our whole data set and use the remaining data points for the training, and then calculate the square error on this single data point for test. That's just one run, right? And then we go to the next data point. We take it out and use the remaining for the training and calculate the square error on the second data point. And do it again and again until we go through all the data points. So we have like if you have n data points, we have n square errors, right? Then we take the average of this n square errors. We use this error to indicate the general performance, to compare different models. That's the basic idea. So, for example, if we only have 5 data points, so we have x1, y1, x2, y2, x3, y3, x4, y4, and x5, y5, right? So here's how leave one out cross-validation works. So we first take out x1, y1, and then we use the remaining 4 data points for training. For example, to fit a 10,000 polynomial, right? Use these 4 points. And then we use this, we use our estimated order 10,000 polynomial to predict this single data point, x1, y1. We got a squared error, right? So we denote it by SE1. This is one run. And next, we take out the second example, x2, y2. And then we use the remaining data points for training, like x1, y1, x3, y3, x4, y4, and x5, y5. We use these 4 data points to train our polynomial regression model, and then use our trained model to predict error on x2, y2. So get the second square error, which is denoted by SE2. Right? So we can continue to go through each of these 5 data points. So we end up with 5 square error. Right? So each square error is actually evaluated on a single data point. And the remaining data points are all used for training. And finally, with average of these 5 square errors, we use this average square error of our SSE on test to indicate the general performance of our model. That's the one out cross validation. So
in each round of training, do we learn a brand new model, or we use the model we have previous?
Each round of training, you give a specified order polynomial p. For example, if I want to test the general performance when I use like 3 order polynomial, right? So we can set p equals to 3, and then we conduct 5 rounds, right? Each round we use p equals to 3, and the first round we use x2 to x5 for training to get our 3rd order polynomial, and we get a test on x1, y1, we get SE1, right? And in the second round, we fix x2 and y2. We take it out for a test and use the remaining 4 points to estimate another 3rd order polynomial.
Okay. During the second round, we change another way back.
Of course, because your training data set is different.
Okay.
Yeah. And similarly, for x3 and y3, you train another 3rd order polynomial regression model, and you get SE3, right? And you continue, you get 5 SEs and average them. And you get the average SE to indicate the general performance when you use a 3rd order polynomial regression model for training. And of course, you can test whether when you choose a 4th order polynomial is better. Then you execute the similar procedure to get another average SE. You just compare their average square error, and which one is smaller, meaning that which one is better. Any questions so far? Great. So let us stop here.